This question is about lightning discharge, and the first part is define electric field strength. So electric field strength is the force per unit charge acting on a positive test charge, or you could say acting on a point charge. So that's your definition. If I wrote that in terms of symbols, that's force divided by Q. This is the Q. This is the charge of the test charge. It's this formula over here, and when we have got a electric field due to a point charge, another point charge, we're going to combine it with that. When we've got the electric field due to parallel plates, something like this, where we've got V and this is your distance D, then your E is equal to V over D, your electric field strength. Then it says a thundercloud can be modeled as a negatively charged plate that is parallel to the ground. The magnitude of the charge in the plate increases due to the process in the atmosphere. Eventually a current discharges from the thundercloud to the ground. On the diagram, draw the electric field pattern between the thundercloud base and the ground. So this is the electric field pattern for parallel plates. Now I'm doing this firstly, the direction of the electric field is in the direction at a positive charge. So between plates we've got something like that, so we'd have our arrow in that direction. Now it's uniform, so therefore our lines that we draw need to be evenly spaced in between, something like that. Using a ruler would really be good. On the outside though, you get a curving effect. You get a curving effect on the outside, and you want to have an arrow. So you need to take some care with this, make sure that it looks like, firstly, that these are evenly spaced. Maybe have another one in there like that. Don't know if that would have helped. Something like that, evenly spaced, the arrows in the correct direction, and you have this curving at the end here, like that. Those would be your 3 marks for this. It then says the magnitude of the electric field E between two infinitely charged parallel plates is given by the expression here, that E is equal to sigma over E0, where sigma is the charge per unit area on one of the plates. The thundercloud carries a charge of magnitude 35 coulombs spread over its base. The area of the base is 1.2 times 10 to the 7 meters squared. Determine the magnitude of the electric field between the base of the thundercloud and the ground. Okay, so we're going to use this formula over here. They've defined it for us as equal to sigma over E0. And we have, for this, we are going to be firstly working at our sigma, because it says that sigma is the charge per unit area. So sigma would be our charge, which is 35 divided by 1.2 times 10 to the 7. So from that would get about a value of 2.917 times 10 to the negative 6, and that would be coulombs meters to the minus 2. Now our E0 over here is a value that we have in our data booklet. So if you can just remember this, or I'm going to have to get rid of it and I'll come back to it, but if I go back in my data booklet to my E0 value, it's this value over here. So you really need to know what's on your fundamental constants. So that is going to be when we're working out our E, which is equal to sigma. Now we worked out what sigma is. That's equal to 2.917 times 10 to the negative 6. And we're going to divide that by E0, which is our permittivity of free space, which is 8.85 times 10 to the negative 12. When I do that, I get an answer of 3.3 times 10 to the 5. And in looking at this here, I've got this unit here is c squared n to the minus 2 meters to the minus 2, and the sigma here was c, and it was meters to the minus 2. So my meters to the minus 2, meters to the minus 2 are going to cancel, and so I'm going to get a unit, my n to the minus 2. I've got n to the minus 2, that's going to go to the top and it become n squared, and I'm going to have a c divided by c squared. I'm going to get a c to the minus 1, so that will be my unit. State 2 assumptions made. Well, obviously one assumption was that the edge or the bottom of the thundercloud was parallel to the surface of the ground and also we also took this over here. This is the permittivity of free space. Now we are therefore saying that E0 is the permittivity of air. So we made that assumption also. Then it says 3, when the thundercloud discharges, the average discharge current is 1.8 kiloamp. Estimate the discharge time. Now let's just close this and let's just go back to where we were. So here we are here. Now here I've got my I is equal to Q over T. So we've got here that it's 1.8 kiloamp is our current, so I is equal to 1,800 amps, and we want to work out the discharge time. So from this formula over here, we're going to get the time is equal to your Q divided by your I. So we're going to get the Q was 35C divided by 1,800 amp, and we will get from that our time, which turns out to be 20 milliseconds. 20 times 10 to the negative 3 seconds. Finally, we get this question over here. It says the potential difference between the thundercloud and the ground before discharge is 2.5 times 10 to the 8V. 2.5 times 10 to the 8V. Determine the energy released in the discharge. Well, for this we know that V is equal to W over Q. We've got this formula over here. So we want to work out the energy. So we've got W is equal to V times Q. Now we know our Q is equal to 35. Now just a question on the V, because here we start off here where you've got a potential difference across these. Here is 2.5 times 10 to the 8V, but what's going to happen is that as it discharges, as your current flows, so you're getting a discharge there, so an equalization, this potential difference is going to drop to 0. At the end it will be 0 volts. So the average potential difference during this transfer of charge is actually going to be 1.25. So we're actually going to multiply this value by 1.25 times 10 to the 8 volts. And from that we get 4.4 times 10 to the 9 joules. This formula obviously is your definition of your potential difference. Your volt is the work per unit charge, and so we could use that as our formula